Hello, everyone, and thanks for tuning in. Today, we are talking about a true heavy hitter in the world of astronomy. We are discussing a visitor that traveled light years to get here.
That's right. We're talking about the interstellar object known as 3I-ATLS. But we aren't just talking about spotting it with a regular telescope. We're talking about seeing it in a way that has never been done before for an object like this, through X-ray vision.
Exactly. This is a major breakthrough. Just recently, the Japanese Aerospace Exploration Agency, or JAXA, reported the first ever X-ray detection of an interstellar object.
Now, just to set the stage here, when we say interstellar object, we mean something that didn't form in our solar system, right? Like Oumuamua or Borisov?
Precisely. It came from another star system entirely. Now, usually, astronomers look at these things in visible light, infrared, or radio waves. In fact, until this report, 3I ATLS had only been seen in those standard bands, but capturing it in X-rays, that is a pioneering moment.
And to do it, JAXA used a specialized satellite called XRISM, that stands for the X-ray Imaging and Spectroscopy Mission.
Right. XRISM has a telescope on board called Xtend. Think of Xtend as a high-tech camera with a really wide field of view. It uses an X-ray CCD camera to catch incoming X-ray photons.
So what did this X-ray camera actually see? Was it just a tiny dot?
Actually, it was much more impressive than a dot. The images revealed a massive, faint glow. We're talking about an emission halo extending out to 400,000 kilometers from the object's nucleus.
400,000 kilometers? That is roughly the distance from the Earth to the Moon. That is a massive cloud for one object.
It really is. The image itself spanned a projected square of about 3 million kilometers, so this wasn't a small event. But getting this image wasn't easy. It required some incredible timing.
Yeah, I was reading about the logistics of this observation. It sounds like a logistical nightmare.
It was. So 3I ATLS reached its brightest phase, its perihelion, on October 29, 2025, but the team couldn't look at it then.
Why not? If it was at its brightest, wouldn't that be the best time?
You would think so, but it was hidden behind the sun from the perspective of Earth-based satellites. Plus, the XRISM satellite has safety limits. It can only observe parts of the sky that are more than 60 degrees away from the sun. If they point it too close to the sun, it could damage the instruments.
Ah, I see. So they had to wait for the object to drift into a safe zone.
Exactly. They conducted a target of opportunity observation about a month later, specifically from late on November 26th to November 28th, 2025.
And that was a long exposure, right?
Very long. The total exposure time was 17 hours. And here's a fun detail about the engineering challenge. ATLS was moving across the constellation Virgo during this time. It wasn't sitting still.
So the satellite had to track it.
Yes, but not just a simple pan. They had to adjust the satellite's altitude 14 times, basically every 3 hours, just to keep the object near the center of the Xtend instrument's view.
Impressive. That is some serious precision. So after all that effort, they get the data back. They see this 400,000 kilometer glow. But here's the big question. Why is a rock from another star system emitting X-rays? It's not a star itself, so where is the energy coming from?
That is the fascinating part. It's actually similar to something we discovered back in 1996 with Comet Hyakutake here in our own solar system.
Okay, so comets can give off X-rays?
They can. And the leading theory for ATLS is a process called charge exchange.
Charge exchange. Can you break that down for us?
Sure. Picture the sun constantly blowing out a stream of charged particles, the solar wind. Now, ATLS is surrounded by a huge plume of gas. We know that gas is there because the SphereX Observatory and the Webb telescope detected it back in August 2025.
Okay, so we have a cloud of gas around the object, and the solar wind is smashing into it.
Exactly. When the charged particles from the solar wind collide with the neutral atoms in that gas cloud, they steal electrons. This exchange of charge puts the solar wind ions into an excited state. As they calm back down, they release that extra energy as X-ray photons.
So the glow is basically the solar wind interacting with the object's atmosphere. It's like a cosmic spark.
That's a great way to put it. And the data backs this up. The Xtend spectrum showed excess emission components specifically associated with carbon, nitrogen, and oxygen.
And they're sure that signal came from the object, not just background noise?
They are quite confident. The signal was distinct from the background X-ray emission of the Milky Way galaxy and distinct from Earth's atmospheric emission. It's a clear chemical fingerprint of that interaction.
That is incredible. It really turns Xtend into a natural laboratory. Because of its large mass and that extended coma, the gas cloud, it was the perfect target to test if interstellar objects behave like our local comets.
And it seems they do. This confirmation opens the door for so much more research. Now that we know we can detect X-rays from these visitors, other research teams are going to want to take a look.
Definitely. It would be really interesting to see if there are other X-ray features hiding in that data. Maybe things that don't fit the standard charge exchange model.
Right. Are there unique signatures because it's from a different solar system? We don't know yet. But this pioneering detection by JAXA and the XRISM team has officially started a new chapter in how we study these interstellar travelers.
It's amazing how much we can learn just by looking at the sky in a different light, or in this case, a different spectrum.
Well said. We will keep an eye on any follow-up papers from this discovery. It's an exciting time for astrophysics.
Absolutely. Thanks for listening, everyone.
See you next time.